Hello, we are talking about electrostatic fields in materials, and this is a fun one I got for us here. They're all fun, right? This one we're going to apply Maxwell's equations to some things that we already know from physics, like refraction, the law of refraction, Snell's law, and also electrostatic shielding. If you have a circuit and you put it inside a conductor, then that circuit is electrically isolated from other circuits. Why does that work? Also, if you are familiar with the concept of a Faraday cage, it's something similar regarding shielding, then you'll know it and you'll be able to understand how that works as well after the end of this video. So we're talking about boundary conditions formally, and the idea here is to discover how electric fields behave across an interface or a boundary of two different materials. And we're going to do that by applying Maxwell's equations to the boundary. So what I mean by that is this. Let's say we have some surface or interface. So here's my interface. And this thing is separating two different media or materials. So we're going to call material 2 to be down here. So anywhere down here is material 2, and anywhere up here is material 1. And they're different. They have to be different. They can't be the same. Otherwise, there really is no interface at all. And different in electromagnetism means that, or at least for electrostatics, different means they have different permittivities. So we're going to represent those permittivities of as epsilon 1 and epsilon 2 for materials 1 and 2 respectively. Now the idea is this. We can apply boundary conditions when we know the electric field in one material. How do we get the electric field in the other material? Okay, so here's, let's say, electric field 2 in material 2. Maybe we know that, and we're trying to figure out what would the electric field be in material 1. All right, that's a problem for boundary conditions. How are electric fields 1 and 2 related to one another? We're going to use Maxwell's equations to solve this. And the idea is that we're going to decompose each of the electric fields into normal and tangential components to the surface, that is, the interface. So we're going to call this, right, the normal component. So I'll give that a subscript 2n in material 2, normal component. And then this one would be E2t for tangential to the surface or the interface. And then similarly, I guess that's not a great picture, but we would have E1 normal. My drawings are not very good, I apologize. And then E1 tangential, like that. So we're deconstructing them as the vector sum of a tangential and a normal component. Now, the Maxwell's equations that we have so far, let me remind you, look like this. This one says the circulation of an electric field is equal to 0. That's can be interpreted as Kirchhoff's voltage law. And that's the integral form of that equation. And the point form is that the curl of E is equal to 0. So that's considered to be one Maxwell's equation. Then the other one that we've seen so far is that the closed surface integral of the electric flux density is equal to the charge enclosed by the surface. That was Gauss's law in integral form, and in point form that's the divergence of D is equal to the charge density, like this. So we're going to apply those equations to our problem up here. And the way we're going to do that, I'm going to show this same interface but with less detail now. So here's the interface, and we're going to begin by constructing a very small closed path centered across the boundary. So here's my small closed path, and we'll give some arrows like this, and we'll call A, B, C, D. Okay, and we'll give some dimensions to this thing. We'll call this delta H, and we'll call this delta W, height and width. So just seeing that setup, which Maxwell's equation do you think we're going to apply here? The answer is going to be this one here, the closed line integral, the circulation. All right, well, let's do it. All right, so we're applying this equation. Now, if this thing is small enough, this little loop that I've drawn is small enough, then, and we can make it as small as we want, we're talking about then a small loop, and so that E1 tangential, so this is just, when I do the dot product, remember, I get a scalar. So the tangential is, of course, tangent, it's in the same direction as the width. So we're talking about material 1. So from A to B, I've got the electric field in the tangential direction. That's E1 tangential times the length of segment AB, and that's delta W. So that's the first of 4 segments. Then I go against the electric field, right? Because E1 normal is up. So I'm going to have minus E1 normal. Then I'm in material 1 only for half the time. So this would be half the space, I guess. Delta H over 2. Then to complete that segment BC, I'm going against electric field 2 normal. So minus E2n times delta H over 2. Then from C to D, I'm going against the tangential in material 2. So this is minus E2t, but all the way, so times delta W. Then to go from D to A, I'm going to add E2 normal delta H over 2 with E1 normal delta H over 2. And then according to this Maxwell's equation, that should be equal to 0. So that's the circulation of E around this little loop that I have. That's equal to 0. So do any terms cancel here? Looks like we have E1n, those guys cancel, and then E2n, those guys cancel. And so what I'm left with, I can factor out delta W, and I get E1 tangential minus E2 tangential, and then all of that equals 0. Now delta W is not 0, so this implies that inside the parentheses is 0, and so we get kind of our first result, intermediate result, that the tangential components of the electric field across the interface do not change. The electric field, the tangential component of the electric field in interface 1 is equal to the tangential component of the electric field in in material 2. That's pretty cool. Now, let's try to figure out how we're going to get the normal, how the normal components are related. So for that, let's again look at the interface. There's my interface with just not as much detail. And so what I'm going to do, I guess this interface has some depth to it. I'm going to put a Gaussian surface. I'm going to use a cylinder as a Gaussian surface. And that cylinder has cross-sectional area, we'll say delta S. And then this has a height of delta H. Right, and this is my interface, this rectangular thing. So now I'm going to apply the second Maxwell equation, Gauss's law. So we're taking a very small cylinder, and this small cylinder is normal to the boundary, right? And we're going to use this as a Gaussian surface. So we're applying this equation. So we have then d1n, so that is the normal component of the electric flux density in material 1, times delta S minus that in material 2 times delta S equals the charge enclosed. So why is that? Well, through the bottom surface is the normal component is the only thing that causes flux through the bottom surface. The tangential component does not have any flux through the bottom surface. So the normal component, material 2, is there, right? But that because that enters that's inward going flux, so that's a minus sign. So and because it's normal, we can drop the dot product and just take the d2n times the surface. Then in material 1, we have outward going flux, which is positive. So d1n, for the same reason, times delta of S. Now the tangential stuff, the cylinder, of course, has a side as well, a curved side. And so the tangential stuff, the tangential components, they enter the cylinder, but they also leave the cylinder. So they create zero net flux. So we don't even have to write them here in this closed surface integral. Great. So now we can factor out delta S, divide by delta S if we want. And this is the charge enclosed. So on that sheet, on the interface, divided by the surface area, so that's the surface charge density, right, on the part of the sheet that is enclosed by the cylinder. If no free charges are placed on that interface, then this is equal to 0. And what we have is the normal components of the electric flux density are equal to one another. And remember the relationship between the flux density and the electric field. So bringing in that relationship, remember that D is equal to epsilon times E. Then we have epsilon 1, the permittivity, times E's normal component is equal to epsilon 2 times E's normal component, like that. And thus what we've done is we've found the relationship between the electric field normal components then, right, by applying Gauss's law. Pretty cool. So what we would say here is that, going back to the first equation that we derived, we would say that the tangential component is continuous at the boundary because it does not change. But the normal component does change. It changes in this ratio of the permittivities. And so we would say that the electric field normal component is discontinuous. Right? So the tangential component of the electric field is continuous. The normal component of the electric field is discontinuous. How about D? pause the video if you want to think about it. What would we say about D in this case? All right, well, hopefully you paused. D's normal components are continuous because they do not change. And then if we back substitute with epsilon and so forth, we would see that D's tangential components are discontinuous. All right. Now, let's go back to the tangential part. And if we substitute, or if we use some geometry, the tangential component of E1 is E1 times sine of theta 1, where theta, let me just indicate theta. So if here's the normal to the boundary, here's theta 1 and here's theta 2. Okay, so if we have an electric field whose magnitude is E1, then the tangential component is E1 sine, because sine is related to the opposite of theta 1. So then we would have, and for the same argument, we would have equals E2 sine theta 2, like this. And I'm going to put some asterisks there. We're going to come back to that equation. Now let's look at the normal components. For a similar reason, I could have epsilon 1 times E1 cosine theta 1 equals epsilon 2 E2 cosine theta 2. And put some asterisks there. Now, if I divide the first equation with asterisks by the second equation, E1s will drop out, E2s will drop out, and the sine over cosine becomes tangent. And what I get by dividing those equations is 1 over epsilon 1 times the tangent of theta 1 equals 1 over epsilon 2 times the tangent of theta 2. In other words, if I rearrange that, tangent of theta 1 over tangent of theta 2 equals epsilon 1 over epsilon 2. That's cool. That's called the law of refraction. In physics, you call this Snell's law. And this tells you then how the angles of refraction, or how the angles, or how the electric field is bent across the interface, are related to one another, and they're related with the tangents and with the permittivities of the materials. Pretty cool. So, while the boundary conditions are usually used to find the electric field on one side, when you have the other side, we can also apply boundary conditions then to find the bending, right, of these flux lines across the boundary. Very cool. All right, now I'm going to erase that a little bit. Let's see, what do I need? Yeah. I'm gonna erase Snell's law there. Make sure you write that down if you haven't already. Now, let's talk about some special cases. We just did the general case. Let's say we have a conductor dielectric interface. All right, well, recall that if there's no electric field inside a perfect conductor. So if we were to apply this equation here, one of the electric fields is 0. And so we don't really need subscripts 1 and 2 anymore, because just one of them is 0 and the other one is just the other one. So what we would end up have happening is we would get this: the normal component of the non-zero electric field times delta H over 2 plus the tangential times W minus the normal component over 2 is equal to 0, right? So imagine here, this way, this way, this way. I don't have to consider the other material because the electric field down here is 0. So this thing implies, after you cancel this and you cancel this, that the tangential component is 0. That's pretty interesting. So in the material that does have an electric field, its tangential component is 0, which means it only has a normal component. Now, if we applied Gauss's law, this one, for a similar reason, or with a similar argument, there's no electric field in one of the materials. So this is the cylinder argument that I erased, but we would have this. And then if we bring in the electric field instead of the electric flux density, we would have this. All right, so there are some important points for this particular situation. When one of our materials is a perfect conductor and the other material is a dielectric. So in a previous video we had said that no electric field exists within a conductor. Right? So we just use that fact here. And then remember that rho v equals 0 inside a conductor, and again, the electric field is equal to 0. Both of those things are true. Second important point, and we also said this in a previous video, but I want to just emphasize it here. Since the electric field inside a conductor is equal to 0, and that's related to the potential difference between any 2 points in a conductor, then that means the potential difference between any 2 points in a conductor is 0. Okay, and the third important point here, and now this is a new point, what we just found, the tangential component to a conductor, the tangential component of the electric field in the dielectric material, when the other material is a conductor, must be normal, or the tangential component is 0, so the electric field must be normal. So that means that E external to a conductor must be normal to the surface of the conductor. All right, let me erase some things here. So this is good news, because we've already looked at, well, we looked at conductor free space interface, where we saw a conducting sphere. We calculated the electric field due to a conducting sphere. So this was a perfect conductor, and this was free space. So in free space, that's like this situation, except epsilon gets replaced with epsilon 0. Okay, so the boundary conditions would just become the tangential component is 0 and the normal component is rho s over epsilon 0. And remember, when we looked at a conducting sphere in free space, we found that the electric field pointed radially outward, i.e., it's normal to the surface everywhere, the electric field that is. And so that's what we just found. Point 3 here, E external to a conductor must be normal to the surface of the conductor. So that agrees with previous results that we have. Finally, and this is cool, let's talk a little bit about electrostatic shielding. Since E, the electric field, is equal to 0 inside a conductor, conductors can be used to shield one circuit from another. So for example, if I have circuit B here, and then I encapsulate that with some sort of conducting shell. Okay, so here's a conducting shell. So we're going to call this circuit, B. We're going to call this conducting shell A. And then maybe we have a circuit C over here. Now the way it stands then, if I ground the conducting shell, the electrical properties of circuits B and C are completely independent of one another. Each B and C is shielded by conductor A. Again, and that's because the electric field inside a conductor is 0. So any electric field that C is generating has no effect on B, because its electric field is 0 inside the conductor, and any electric field that B is generating for the same reason does not get out of A, so it does not influence C at all. So that's electrostatic shielding, and in some cases this surrounding shield is called a Faraday cage. So we might refer to A as being a Faraday cage, and there are some great videos online about Faraday cages and electrostatic shielding. All right, so hopefully you enjoyed that. That's one of my favorite topics in electromagnetics. So we're gonna still stick with electrostatic fields in materials in the next video. So I'll see you then.